Can you recall how we did it in the case of linear basis functions? Right. In order to do that, we take the following approach. Right? We use the invertibility of our mapping. Okay? And what is the mapping we're talking about? It is the fact that the geometry is mapped as follows, right? X over element E is also written, parameterized by the coordinate in the parent unit domain, right? And the way we do this is to actually use the same basis functions as we use for our trial solution and weighting function, right? So we have NA parameterized by XC times XAE. And you recall what these are. What are they? Right, they are our nodal coordinates in the physical domain or physical space. Right, and this is the fact of the isoparametric mapping. Okay, isoparametric because we are using the same parametrization for the trial solution and weighting function as well as for the geometry. Right. Okay. What that lets us do is the following, right? What this implies for us is that over element E, we have x comma c is now sum A going from 1 to 3 n A comma c times xae, right? But just on the previous slide, we've computed NA comma C for A equals 1, 2, 3. Right, there it is at the bottom, right, the last three equations. So let's use those. We get here, I'm going to write out the sum explicitly. Okay, we have N1 comma C C1e plus N2 comma C C2e plus N3 comma C X3e. We have N1, N2 and N3 derivatives with respect to C. So that turns out to be 1/2 1 minus 2C times x1e minus 2c times x2e plus 1/2 1 plus 2c times x3e. All right. Now, what I'm going to do is note that there are just two constant terms here, that is terms independent of C, and those are the ones. I'm going to pull those constant terms aside first. x3e minus x1e divided by 2. The other terms depend upon C, okay, and those terms are the following. I have from here multiplying x1e, I have let me see, I'm going to write all of this as multiplying C, right, because the only other term is linear since we've taken a derivative over quadratics. All right, for x1e, if we just look at that second to last line, we get minus x1e. For x2e, we get minus 2 x2e. And for x3e, we get plus x3e. Okay? I see that I may have made a algebraic error on the previous slide, so let me just go back here. Right, if I look at our quadratic basis functions, I observe that I have c times 1 minus c. I really need to have a negative sign inside of this. Okay, so I need to have a negative sign here. Okay, that works out now. And then what happens here is that I pick up a negative sign here as well. And when this all works out, this sign changes as follows. Okay, right, that is right now. And then when I come back here, the signs here change. Okay, all right, now everything works out fine. So this becomes plus. Okay, that matters to get things right, because we need to examine what happens with this term here. Okay, and in order to examine what happens with it, let us look at our element more closely. We have omega e, a quadratic element, right, or alternately a 3-node element with quadratic basis functions. All right, the mid-side node, right, the node between let's say x1e, x3e, and x2e, right? That node, remember, is obtained from a mapping. That node, or indeed the entire element, is obtained from a mapping from a bi-unit parent domain in which the coordinates are c equals -1, c equals 0, and c equals 1, right? What that means is that x2e is a mid-side node, implying that the position of x2e is the position of x3e plus the position of x1e divided by 2. If it is a mid-side node, that must hold, right? But then this implies that in our expression for x comma c equals x3e minus x1e divided by 2 plus c times x1e minus 2x2e plus x3e, we see that this is equal to 0, okay, because of that result. On the other hand, this is what we can now once again denote as HE over 2, right, because HE is the length of the element, right, which is just the distance between the last node on the element and the first node on the element, which is x3e minus x1e, if one just looks at that figure again. Okay? What this tells us then is that because of the invertibility of the map, okay, the fact that this map is invertible implies that c comma x equals 1 over x comma c. Okay, that's what invertibility tells us. Okay, which is just 2 over HE. So we have a very straightforward way to compute our gradients. All right. What we're seeing is that even though we have quadratic elements, the essentially the element length, right, is still given, of course, by the distance between the last node and the first node. Okay, and indeed, even our so-called tangent of the map, which is x comma c, right, it remains equal to HE over 2, which is a constant, right? So what we're saying is that the tangent of the geometric map is constant, right? This follows because the mapping that we have is also what is called an affine map. Okay, right? So with all of that in place, what we observe is that now we have a very straightforward approach to computing this integral. Okay, so integral over omega e wh comma x ea uh comma x dx now is integral over omega e sum over a na comma c comma x, but c comma x we've just concluded is 2 over he times c a e, and this is how we write wh comma x. We get ea, and for comma x we have sum over b nb comma c comma x once again is written as 2 over he d b e dx. Okay, we're essentially able, as we did in the case of the linear basis functions, to reduce our gradients to gradients in terms of c. And therefore, we're able to express this entire integrand in terms of our coordinate in the parent bi-unit domain, which is c. All right. This is a good place to end this segment. When we return, we will proceed with the computation of the other parts of our finite dimensional weak form.